So we're looking at page 7, and we are looking at two topics that are important that you understand, but that we probably will use less. Mass, we devoted 2 videos to it and a couple of pages in the notes, very important. These ones, while they're still important to understand, they're harder to measure in the lab, harder to use. And so we're spending less time with these. They will be emphasized less. So we can express quantities in terms of representative particles. And you'll recall this from the unit on moles. A mole is a specific number of particles. But if we want to relate 2 different substances, the quantities have to be converted to moles. Moles is the only thing that 2 different substances will have in common. Once the quantities are converted to moles, then we can use the mole ratio. Here's something as a note. Representative particles are the only calculations that use Avogadro's number. So if it asks for atoms, molecules, formula units, or ions, this is applicable. Otherwise, you will not use Avogadro's number. So calculate quantities of substances based on representative particles. For this one, we are using the Haber process. And you'll notice that I'm not calculating molar masses right now because none of these actually relate to mass. We're talking about moles and molecules and really nothing else. So I'm going to give you a brief instruction on how you would do these. If you understand moles as a concept pretty well, this is going to make a lot of sense and you'll catch on pretty quickly. How many moles of ammonia can be produced from 3.23 times 10 to the 24th nitrogen molecules? So I'll start with my given number, given value, it's nitrogen molecules. And in order to relate 2 substances, we are converting to moles. So dividing by Avogadro's number, and that is 1 mole of nitrogen. Now that we are in moles, we can relate nitrogen and ammonia with the mole ratio. According to the balanced chemical equation, for every 1 mole of N2, we get 2 moles of NH3. Now, if you read the question carefully, this is asking you for how many moles of ammonia, and here I have moles of ammonia. So at this point, I'm going to stop. I'll go ahead and put it into my calculator. If you're using a school issue calculator, you'll want to be very careful to put these in parentheses. If you don't put them in parentheses, the calculator will, for some reason, multiply the base and your answer will be excessively large. Here's what I'm looking at. This has times 10 to the 23rd. This one has times 10 to the 23rd. Since we're dividing, we can just get rid of those. And it's really 3.23 divided by 6.02 times 2. We'll go ahead and put this into our calculator. We're going to start with our given value, 3.23 times 10 to the 24th, and that is nitrogen molecules. And the first thing we have to do is convert it to moles. In order to do that, we're going to divide by Avogadro's number. And that will tell us moles of nitrogen. Now that we are in moles, we can use the mole ratio, comparing moles of nitrogen and moles of ammonia. The balanced chemical equation tells me that for every 1 mole of nitrogen, I am getting 2 moles of ammonia. Something to consider is that if you're using a school issue calculator, there is something slightly off with the order of operations when you do scientific notation. You have to put scientific notation in parentheses. Otherwise, rather than dividing the base, it will multiply the base, and you'll get the same coefficient, but you'll end up with something that is times 10 to the 46th or 47th, which is not correct. It should be, so 10 to the 24th divided by 10 to the 23rd is just 10 to the 1st. So really what's going on is, let's go ahead and put it in our calculator. Be careful to use the parentheses. And you should see that it's very close to 10. It's 10.7 moles of ammonia. How many ammonia molecules can be produced from 2.36 moles of hydrogen gas? We are starting in moles, which means we can go straight to the mole ratio. We are relating moles of hydrogen with moles of ammonia. And our coefficients, 3 for hydrogen, 2 for ammonia. But it wants to know how many ammonia molecules. And in 1 mole of ammonia, we have 6.02 times 10 to the 23rd molecules of ammonia. Again, just as a habit, I would put this into parentheses just to make sure that nothing interferes with the order of operations, and we'll find 9.47 times 10 to the 23rd, and that's ammonia molecules. How many nitrogen molecules were used to produce 4.52 times 10 to the 22nd molecules of ammonia? We will start with our given value. Convert it to moles. Here's the mole ratio, 2 moles of ammonia for 1 mole of nitrogen. It wants to know how many nitrogen molecules. And if you're looking carefully, you might be saying that I'm doing more work than I really have to, which is actually true. But it's important to have it on paper, because if we don't put it on paper and we make a mistake, it's really hard to figure out what happened. And so I think it's best just to write things down the first time. Here's what we're looking at. First off, when you put this in your calculator, 4.52 times 10 to the 22nd needs to go in the parentheses. And before you go typing all of this in the calculator, you'll see that you have Avogadro's number on the bottom of one fraction and the top of another, which will end up canceling each other out. So really we have this given value divided by 2. So we have 2.26 times 10 to the 22nd. And this is molecules of nitrogen. The next idea is molar volume, which we also discussed in the unit on moles. Remember this. As with other measured quantities, calculations may begin using the volume of a gas at STP. Using our conversion between moles and volume of gas requires specific conditions. And it was 1 atmosphere and 0 degrees Celsius. If these conditions are both met, then 1 mole occupies a volume of 22.4 liters. If these conditions are not met, then we have to use a more complex calculation, which we'll talk about in a later unit. We are using the Haber process again, since it has gases and we are familiar with it. So how many moles of ammonia can be produced from 25.0 liters of hydrogen gas at STP? Now this type of question is important because a lot of times we measure gases in terms of volume. Like if you blow up a balloon, you can measure the volume. It's not the easiest thing, but you can do it. So add STP, and actually it says add STP here, so it even applies to this one. 22.4 liters per mole of hydrogen gas. And we are comparing hydrogen with ammonia. So we're ready for the mole ratio, 3 for the hydrogen, 2 for the ammonia. It comes out to be 0.744 moles of ammonia. Going the opposite direction, if we know how many moles of nitrogen gas, we want to know what volume of ammonia can be produced at STP. We will be using the mole ratio first because we are already in moles. Coefficients are 2 for the ammonia, 1 for the nitrogen. And now we're looking for volume. So 1 mole of ammonia is 22.4 liters. And this comes out to be 140 with a decimal point for 3 significant figures, liters of NH3.